Hello everyone, my name is Sandeep Banik. I'm a PhD student from Michigan State University. I'm here to present our paper titled FlipDyn, a game of resource takeover in dynamical systems. This work was done with my advisor Dr. Shaunak Deepaparthikar. This research was supported in part by NSF Award under the Secure and Trustworthy Cyberspace program. I will first begin by demonstrating what exactly does a takeover mean in dynamical system. Imagine an office space shared between you and your colleague acting as an adversary. Now you come to the office at 9 a.m. and set the thermostat temperature to some desired value. At 10 a.m. you continue to do your work. At 11 a.m. you go and check the thermostat temperature. Time passes by. Then around at 1 p.m. your sneaky colleague comes and changes the temperature. At 2 p.m. you get annoyed and both of you move towards the thermostat. However, it remains fixed to the temperature set by your colleague. Now at 3 p.m. you get annoyed and go and change the temperature to the desired value. This goes on till the end of the day, let's say 4 or 5 p.m. In this scenario, there are regions in which either you or the adversary has completely taken over the system or resource. The resource here is the thermostat, and the dynamics is how the room temperature changes over time. We assign a variable alpha to such a resource known as the FlipDyn state. We assign a value of 0 when you or the defender is in control and a value of 1 when the adversary is in control. Therefore, given such a setup of a finite horizon decision-making problem of controlling the FlipDyn state, we need to decide when should the defender take over versus an adversary. Given the FlipDyn game, we will go over the rules of the game. The realized discrete defender action at time k is assigned the variable alpha k0, 0 being idle and 1 being taking over the dynamical system. Similarly, we use alpha k1 to represent the discrete action of the adversary at time k. We begin by describing the first rule of the game. A player takes over the dynamical system when it acts on it while the other player is idle. This can be seen in the example at 9 a.m. Next, the player is in control, remains in control. We see that at 10 a.m. when both are idle and the defender remains in control of the dynamical system. Now, a change in the FlipDyn state is observed at 1 p.m. when the adversary acted and the defender remained idle. Finally, when both the players act to take over, the FlipDyn state remains unchanged. We see that at 2 p.m. when both the players acted, but the FlipDyn state does not change. All these rules can be encoded in such a conditional statement based on the actions of the player. This work is inspired from the FlipIT setup, which is a two-player game between an adversary and a defender to take over a shared static resource. Compared to the dynamical system, the resource here is static, like a computing device, virtual machine, or a cloud service. The FlipIT has been extended to multiple resources known as FlipDyn. Here, the players have to decide when to take over a single resource via a OR operation or take over multiple resources via an AND operation. There have been some works in designing an adversary controller versus a contractive controller in a periodic setting. Compared to our current setup, here the objective is to solve for the control policy in a known periodic setting. The references are listed here. Although the war of thermostat may seem silly, such a setup is quite important in a typical dynamical system consisting of a plant, sensor, and actuator. Based on who is in control, the system may remain stable or destabilize, causing disruption of service or potential loss of life. For instance, an actuator might be the pedal of a car, the car representing the plant, and speedometer as a sensor. There are multiple systems which can be represented by such a schematic, such as an electrical grid, and so on. In this work, we assume linear system dynamics, that is, the state varies linearly as a function of the previous state and control. For either the defender or an adversary control, the system evolves linearly. For example, the temperature of the room varies linearly with respect to the previous temperature, weather, and based on either the defender's or the adversary's control. A simple linear representation of the linear dynamics is shown in the figure on the right. Additionally, we assume the defender's control policy is known and fixed, that is, we know how you move in the office to change the thermostat temperature, and this is a feedback controller. Similarly, we also know how an adversary or your colleague moves to change the thermostat temperature. Such an adversary controller might be feedback and fixed as well. Finally, we assume state, defender, and adversary takeover costs are quadratic with respect to the state. Imagine if you have a desired temperature of 72 F and any perturbation like 73 or 71 will cause your annoyance quadratic in nature. In 2 dimensions, that might mean your colleague is notorious enough to not only change the temperature but also the intensity of the lights. With the assumptions stated, we formulate the problem with the objective being a sum of the state and takeover cost from either the defender or the adversary. Therefore, the objective is a function of the state, FlipDyn state, and the takeover actions of the defender and the adversary. The dynamics of the FlipDyn state evolves as a function of the takeover actions of the defender and adversary. The FlipDyn dynamics encodes the rules of the games, indicating who takes over at any given time instance. The defender wants to minimize the objective by choosing when to remain idle or take over, whereas the adversary wants to maximize the same via its choices. Therefore, this is formulated as a zero-sum game. Since this is a finite horizon problem, we aim to find the defenders and adversaries takeover policy over the horizon L, indicating at what times one should take over. We'll look at a pair of policies in Nash equilibrium. A Nash equilibrium can be visualized as finding a saddle point such that neither player has any incentive to deviate from this point. The objective function can be written as a sum of the state, the current takeover cost, and any future cost. The objective function at any given state is known as the value function, indicating how much value does one hold at any given state. Such a value function can be written recursively as state cost and cost to go. Since the value function is dependent on the FlipDyn state, we split it into 2 parts, that is V0 and V1 for alpha is equal to 0 and alpha is equal to 1 respectively. We analyze the components of the value function for the FlipDyn state of 0, as the same method can be used for alpha is equal to 1. We derive the value function as a sum of the state costs and the value of a zero-sum matrix game. The elements of this matrix corresponds to the pair of the actions taken by the defender and adversary. Additionally, the elements of the matrix game are a function of the future state when either the defender or the adversary were to take over. Notice when the defender remains idle and the adversary acts to take over, the entry corresponds to the value function in FlipDyn state 1. Such a zero-sum matrix game, which is dependent on the future state, can be represented using some basic symbols. For such a matrix, we assume the following inequality to hold. In simple terms, this would mean there is enough incentive for the adversary to take over and the defender pays more when trying to take over compared to remaining idle. Such a matrix structure provides us with the expected value of the game with det as the determinant. The expectation is over the probabilistic actions of both the players. We use such a form to derive the value function of the state given by this equation. Such a matrix structure also enables us to derive closed form expressions for the actions of both the players. We will go through a basic derivation of obtaining the expected value of the zero-sum matrix game shown previously. The expected value of a zero-sum matrix as a function of the player action can be depicted in this form. Since the actions are limited to only 2 possibilities, we can replace the idle action with the complementary of the takeover action for each player. We multiply the defender action with the entries of the zero-sum matrix to obtain one row 2 column matrix. We aim to find the Nash equilibrium, implying that either actions of the adversary must lead to the same outcome. That is, there should not be any incentive to deviate the defender's policy for any choice of the adversary. This implies both the entries must equate to each other, which provides us with the policy of takeover for the defender. Similarly, we can obtain the same for the adversary. We can plug these back in the expression shown here to obtain the expected value of the game. The probability of taking over by the defender and the adversary is shown symbolically on the right. So you might wonder the problem is solved at this point, but if you notice, the zero-sum matrix is a function of the future state. So we will have to solve such a matrix game for every possible temperature in the thermostat example. This is impractical for high dimension system with continuous state, which creates a need to look for a form for the value function. We assume a quadratic form for the FlipDyn state of 0 and 1. Why? Because we started with the assumption of quadratic state and takeover costs. We analyzed the FlipDyn game for a scalar system. The cost for the FlipDyn game for the state, defender and adversary for the scalar system is shown here. We use the value function form we obtained earlier and plug in the linear dynamics for the scalar system with appropriate dimensions. The parametric form for alpha is equal to 0 in scalar system consists of a scalar pk0 multiplied with a quadratic state. Using both the value function form and the parametric form, we can obtain a scalar recursion for the FlipDyn state of alpha is equal to 0. We notice the state is factored out of the equation, enabling us to compute the value and takeover policy at every stage of the game. A similar recursion can be obtained for the FlipDyn state of 1 with changes in the dynamics and signs. Although we factor out the state in the scalar case, we cannot do this for higher dimensional systems, and we will see exactly why. Such a quadratic form must satisfy both the sides of the value function equation. Plugging in the linear dynamics, we obtain the final value function form as shown here. Therefore, on the left we have a quadratic form, and this needs to equate to the right hand side equation. We notice we can club some of the terms as a quadratic. This is the defender takeover quadratic cos. However, this term, which also happens to be the probability of remaining idle for the defender, becomes a nonlinear function. This prevents us to use a quadratic form on the right hand side. Thus, quadratic form does not satisfy the value function equation because of the coupling of the FlipDyn states. So, what can we do about this? We can make an additional assumption of diagonal takeover costs. A simple example one can visualize is a quadratic takeover cost on the temperature and intensity of light. Notice there is no cross term between the light intensity and temperature. We can use such an assumption to solve for an upper bound of the value function via this inverse. Intuitively, this can be visualized as solving for a large quadratic compared to the left-hand side. Using such a property, we can derive an approximate recursion over the horizon for both the FlipDyn state. Notice the change in the terms and the signs for the alpha 1 quadratic form. We illustrate the solution of the FlipDyn game on a numerical example in two-dimensional system. The defender and the adversary dynamics are shown here. We start with the initial state x0 and the defender in control. The policy of takeover for both the players over a horizon of 100 is shown here. Notice the probability of takeover by the defender is high, except near horizon 75 when the adversary takeover rises. Since we solve for the positive definite quadratic form, we see how the smallest eigenvalue given by lambda n changes over the horizon. If we were to notice for such a pair of costs of d is equal to 0.5i and a is equal to 0.9i, we notice p0 or the quadratic form for the FlipDyn state 0 reaches a steady state, whereas for alpha is equal to 1, it keeps changing and reaches a relatively high value over the horizon. To conclude, the challenge was to take over a common resource under an adversarial presence. The common resource is modeled as a dynamical system. The contributions include modeling a zero-sum game, value function for any general system, solving the defender and adversary policy for general linear dynamical system with quadratic cos. Future directions include inferring the FlipDyn state, that is, here we assumed we knew the FlipDyn state at any given time instance. What if the colleague was stealthy and you didn't know when he changed the thermostat temperature? Adding bounded process and measurement noise. And finally, as opposed to restricting ourselves to a quadratic form, what if we were to use a learning-based method to represent the value function via a more complicated form as shown here? This brings me to the end of my presentation. Thank you everyone for attending my talk. I hope you all enjoyed it.